Cloud computing has 5 fundamental attributes. First, customers get computing resources on demand and self-service. Cloud computing customers use an automated interface and get the processing power, storage, and network they need, with no need for human intervention. Second, they can access these resources over the network. Third, the provider of those resources has a big pool of them and allocates them to customers out of the pool. That allows the provider to get economies of scale by buying in bulk. Customers don't have to know or care about the exact physical location of those resources. Fourth, the resources are elastic. Customers who need more resources can get more rapidly. When they need less, they can scale back. And last, the customers pay only for what they use or reserve as they go. If they stop using resources, they stop paying. The first wave of the trend towards cloud computing was colocation. Colocation gave users the financial efficiency of renting physical space, instead of investing in data center real estate. Virtualized data centers of today, the second wave, share similarities with the private data centers and colocation facilities of decades past. The components of virtualized data centers match the physical building blocks of hosted computing, but now they are virtual devices. With virtualization, you still maintain the infrastructure. It is still a user-controlled/user-configured environment. About 10 years ago, Google realized that its business couldn't move fast enough within the confines of the virtualization model, so switched to a container-based architecture, a fully automated, elastic third-wave cloud that consists of a combination of automated services and scalable data. Google believes that, in the future, every company regardless of size or industry will differentiate itself from its competitors through technology. Largely, that technology will be in the form of software. Great software is centered on data. Thus, every company is or will become a data company. Google Cloud provides a wide variety of services for managing and getting value from data at scale. Virtualized data centers brought you infrastructure as a service, IaaS, and platform as a service, PaaS, offerings. IaaS offerings provide you with raw compute, storage, and network, organized in ways familiar to you from physical and virtualized data centers. PaaS offerings, on the other hand, bind your code to libraries that provide access to the infrastructure your application needs, thus allow you to focus on your application logic. In the IaaS model, you pay for what you allocate. In the PaaS model, you pay for what you use. As cloud computing has evolved, the momentum has shifted toward managed infrastructure and managed services. According to some publicly available estimates, Google's network carries as much as 40% of the world's internet traffic every day. Google's network is the largest network of its kind on Earth. Google has invested billions of dollars over the years to build it. It is designed to give customers the highest possible throughput and lowest possible latencies for their applications. The network interconnects at more than 90 internet exchanges and more than 100 points of presence worldwide. When an internet user sends traffic to a Google resource, Google responds to the user's request from an edge network location that will provide the lowest latency. Google's edge caching network cites content close to end users to minimize latency. Regions and zones. Regions are independent geographic areas that consist of zones. Locations within regions tend to have round-trip network latencies of under 5 milliseconds on the 95th percentile. A zone is a deployment area for Google Cloud Platform resources within a region. Think of a zone as a single failure domain within a region. In order to deploy fault-tolerant applications with high availability, you should deploy your applications across multiple zones in a region to help protect against unexpected failures. To protect against the loss of an entire region due to natural disaster, you should have a disaster recovery plan and know how to bring up your application in the unlikely event that your primary region is lost. For more information on the specific resources available within each location option, see Google's Global Data Center locations. Google Cloud Platform services and resources can be zonal, regional, or managed by Google across multiple regions. Zonal resources. Zonal resources operate within a single zone. If a zone becomes unavailable, all of the zonal resources in that zone are unavailable until service is restored. Google Compute Engine VM instance resides within a specific zone. Regional resources. Regional resources are deployed with redundancy within a region. This gives them higher availability relative to zonal resources. Multi-regional resources. A few Google Cloud Platform services are managed by Google to be redundant and distributed within and across regions. These services optimize availability, performance, and resource efficiency. As a result, these services require a trade-off on either latency or the consistency model. These trade-offs are documented on a product-specific basis. Google was the first major cloud provider to deliver per-second billing for its infrastructure-as-a-service compute offering, Google Compute Engine. Per-second billing is offered for users of Compute Engine, Kubernetes Engine, Container Infrastructure as a Service, Cloud Dataproc, the open-source big data system Hadoop as a Service, and App Engine Flexible Environment VMs. Google Compute Engine offers automatically applied sustained use discounts, which are automatic discounts that you get for running a virtual machine instance for a significant portion of the billing month. Specifically, when you run an instance for more than 25% of a month, Compute Engine automatically gives you a discount for every incremental minute you use for that instance. Custom virtual machine types allow Google Compute Engine virtual machines to be fine-tuned for their applications. Google gives customers the ability to run their applications elsewhere if Google becomes no longer the best provider for their needs. This includes using open APIs. Google services are compatible with open-source products. For example, Google Cloud Bigtable, a horizontally scalable managed database. Bigtable uses the Apache HBase interface, which gives customers the benefit of code portability. Another example, Google Cloud Dataproc offers the open-source big data environment Hadoop as a managed service. Google publishes key elements of its technology, using open-source licenses, to create ecosystems that provide customers with options other than Google. Google provides interoperability at multiple layers of the stack. Kubernetes and Google Kubernetes Engine give customers the ability to mix and match microservices running across different clouds. Secure Boot Stack. Google server machines use a variety of technologies to ensure that they are booting the correct software stack, such as cryptographic signatures over the BIOS, bootloader, kernel, and base operating system image. Premises security. Google designs and builds its own data centers, which incorporate multiple layers of physical security protections. Access to these data centers is limited to only a very small fraction of Google employees. Google additionally hosts some servers in third-party data centers, where we ensure that there are Google-controlled physical security measures on top of the security layers provided by the data center operator. Encryption of inter-service communication. Google's infrastructure provides cryptographic privacy and integrity for remote procedure call (RPC) data on the network. Google's services communicate with each other using RPC calls. The infrastructure automatically encrypts all infrastructure RPC traffic which goes between data centers. Google has started to deploy hardware cryptographic accelerators that will allow it to extend this default encryption to all infrastructure RPC traffic inside Google data centers. User identity. Google's central identity service, which usually manifests to end users as the Google login page, goes beyond asking for a simple username and password. The service also intelligently challenges users for additional information based on risk factors such as whether they have logged in from the same device or a similar location in the past. Users also have the option of employing second factors when signing in, including devices based on the Universal Second Factor (U2F) Open Standard Encryption at rest. Most applications at Google access physical storage indirectly via storage services, and encryption using centrally managed keys is applied at the layer of these storage services. Google also enables hardware encryption support in hard drives and SSDs. Google Front-End, GFE. Google services that want to make themselves available on the Internet register themselves with an infrastructure service called the Google Front-End, which ensures that all TLS connections are terminated using correct certificates and following best practices such as supporting perfect forward secrecy. The GFE additionally applies protections against denial of service attacks. Denial of service (DOS) protection. The sheer scale of its infrastructure enables Google to simply absorb many DOS attacks. Google also has multi-tier, multi-layer DOS protections that further reduce the risk of any DOS impact on a service running behind a GFA. Intrusion detection, rules and machine intelligence give operational security engineers warnings of possible incidents. Google conducts red team exercises to measure and improve the effectiveness of its detection and response mechanisms. Reducing insider risk, Google aggressively limits and actively monitors the activities of employees who have been granted administrative access to the infrastructure. Employee U2FUs. To guard against phishing attacks against Google employees, employee accounts require use of U2F-compatible security keys. Software development practices. Google employs central source control and requires two-party review of new code. Google also provides its developers libraries that prevent them from introducing certain classes of security bugs. Google Cloud Platform lets you choose from computing, storage, big data/machine learning, and application services for your web, mobile, analytics, and back-end solutions. Google Cloud Platform's products and services can be broadly categorized as compute, storage, big data, machine learning, networking, and operations/tools. This course considers each of the compute services and discuss why customers might choose each. This course will examine each of Google Cloud Platform's storage services, how it works and when customers use it. To learn more about these services, you can participate in the training courses in Google Cloud's Data Analyst Learning Track. This course also examines the function and purpose of Google Cloud Platform's big data and machine learning services. More details about these services are also available in the training courses in Google Cloud's Data Analyst Learning Track. You're probably thinking, how can I make sure I don't accidentally run up a big GCP bill? GCP provides 4 tools to help: budgets and alerts, billing export, reports, and quotas. Let's look at budgets and alerts first. You can define budgets at the billing account level or at the project level. A budget can be a fixed limit, or it can be tied to another metric, for example, a percentage of the previous month's spend. To be notified when costs approach your budget limit, you can create an alert. For example, with a budget limit of $20,000 and an alert set at 90%, you'll receive a notification alert when your expenses reach $18,000. Alerts are generally set at 50%, 90%, and 100%, but can also be customized. To help with project planning and cost control, you can set up a budget. Setting a budget allows you to track the growth of your spend towards that amount. This screen shows the budget creation interface. 1. Set a budget name and specify which project this budget applies to. 2. You can set the budget to a specific amount or match it to the previous month's expense. 3. Determine the budget amount. You can set up budget alerts. These alerts send emails to billing administrators after the spend exceeds a percentage of the budget or a specified amount. In our case, it will send an email when the spend reaches 50%, 90%, and 100% of the budget amount. You can also choose to send an alert when the spend is expected to exceed the percentage of the budget amount by the end of the budget period. You can even view spending over time with Data Studio. Data Studio turns your data into easy-to-read, easy-to-share, and fully customizable dashboards and informational reports. For example, you can split your billing reports using your labels. Billing export allows you to store detailed billing information in places where it is easy to retrieve for more detailed analysis, such as a BigQuery dataset or cloud storage. Bucket. Source. https://codalabs.developers.google.com/codalabs/orbitera-gcp-billing/#sign1. And Reports is a visual tool in the console that allows you to monitor expenditure based on a project or services. Source. https://cloud.google.com/billing/docs/how-to/reports. GCP also implements quotas, which are designed to prevent the overconsumption of resources because of an error or a malicious attack, protecting both account owners and the GCP community as a whole. There are 2 types of quotas: rate quotas and allocation quotas. Both are applied at the project level. Rate quotas reset after a specific time. For example, by default, the GKE service implements a quota of 1,000 calls to its API from each GCP project every 100 seconds. After that 100 seconds, the limit is reset. Allocation quotas govern the number of resources you can have in your projects. For example, by default, each GCP project has a quota allowing it no more than 5 virtual private cloud networks. Although projects all start with the same quotas, you can change some of them by requesting an increase from Google Cloud Support. You may find it easiest to understand the GCP resource hierarchy from the bottom up. All the resources you use, whether they're virtual machines, cloud storage buckets, tables in BigQuery, or anything else in GCP, are organized into projects. Optionally, these projects may be organized into folders. Folders can contain other folders. All the folders and projects used by your organization can be brought together under an organization node. Projects, folders, and organization nodes are all places where policies can be defined. Some GCP resources let you put policies on individual resources too, like cloud storage buckets. This course discusses cloud storage buckets later in the course. Policies are inherited downwards in the hierarchy. The resources in a folder inherit IAM policies from the folder. So, if Project 3 and Project 4 are administered by the same team by design, you can put IAM policies onto Folder B instead. Doing it the other way, putting duplicate copies of those policies on Project 3 and Project 4, would be tedious and error-prone. One word of caution: to use folders, you need an organization node at the top of the hierarchy. Here's an example of how you might organize your resources. There are 3 projects, each of which uses resources from several GCP services. In this example, we haven't used any folders, although we always could move projects into folders if that became helpful. Resources inherit the policies of their parent resource. For instance, if you set a policy at the organization level, it is automatically inherited by all its children projects. And this inheritance is transitive, which means that all the resources in those projects inherit the policy too. There's one important rule to keep in mind. The policies implemented at a higher level in this hierarchy can't take away access that's granted at lower level. IAM lets administrators authorize who can take action on specific resources. An IAM policy has a who part, a can do what part, and an on which resource part. The can do what part of an IAM policy is defined by a role. An IAM role is a collection of permissions, because most of the time you need more than one permission to do meaningful work. For example, to manage virtual machine instances in a project, you have to be able to create, delete, start, stop, and change virtual machines. So these permissions are grouped together into a role to make them easier to understand and easier to manage. There are 3 kinds of roles in Cloud IAM. Let's talk about each in turn. In this simple example, a service account has been granted Compute Engine's instance admin role. This would allow an application running in a VM with that service account to create, modify, and delete other VMs. Incidentally, service accounts need to be managed too. For example, maybe Alice needs to manage what can act as a given service account, while Bob just needs to be able to view what can. Fortunately, in addition to being an identity, a service account is also a resource. So it can have IAM policies of its own attached to it. For instance, Alice can have the editor role on a service account and Bob can have the viewer role. This is just like granting roles for any other GCP resource. Virtual machines have the power and generality of a full-fledged operating system in each. You configure a virtual machine much like you build out a physical server, by specifying its amounts of CPU power and memory, its amounts and types of storage, and its operating system. Compute Engine lets you create and run virtual machines on Google infrastructure. There are no upfront investments, and you can run thousands of virtual CPUs on a system that is designed to be fast and to offer consistent performance. You can flexibly reconfigure Compute Engine virtual machines. You can create a virtual machine instance by using the Google Cloud Platform Console or the Cloud Command Line tool. A Compute Engine instance can run Linux and Windows Server images provided by Google or any customized versions of these images. Compute Engine bills by the second for use of virtual machines, with a 1-minute minimum. And discounts apply automatically to virtual machines that run for substantial fractions of a month. For each VM that you run for more than 25% of a month, Compute Engine automatically gives you a discount for every incremental minute. You can get up to a 30% net discount for VMs that run the entire month. Compute Engine offers the ability to purchase committed use contracts in return for deeply discounted prices for VM usage. These discounts are known as committed use discounts. If your workload is stable and predictable, you can purchase a specific amount of vCPUs in memory for up to a 57% discount off of normal prices in return for committing to a usage term of 1 year or 3 years. Suppose you have a workload that no human being is sitting around waiting to finish. Say, a batch job analyzing a large dataset. You can save money by choosing preemptible VMs to run the job. A preemptible VM is different from an ordinary Compute Engine VM in only one respect: you've given Compute Engine permission to terminate it if its resources are needed elsewhere. You can save a lot of money with preemptible VMs, although be sure to make your job able to be stopped and restarted. You don't have to select a particular option or machine type to get high throughput between your processing and your persistent disks. That's the default. You can choose the machine properties of your instances, such as the number of virtual CPUs and the amount of memory, by using a set of predefined machine types or by creating your own custom machine types. You can make very large VMs in Compute Engine. At the time this deck was produced, the maximum number of virtual CPUs in a VM was zone-dependent and at 96, and the maximum memory size was at 624 GB, 6.5 GB per CPU. You can also use a mega memory machine type that scales to 1.4 TB memory. Check the GCP website to see where these maximums are today. These huge VMs are great for workloads like in-memory databases and CPU-intensive analytics. But most GCP customers start off with scaling out, not up. Compute Engine has a feature called autoscaling that lets you add and take away VMs from your application based on load metrics. The other part of making that work is balancing the incoming traffic among the VMs. And Google VPC supports several different kinds of load balancing. Well, consider those in the next section. A managed instance group is a collection of identical VM instances that you control as a single entity, using an instance template. You can easily update all instances in the group by specifying a new template in a rolling update. Also, when your applications require additional compute resources, managed instance groups can do so. Automatically resize the number of instances in the group. Managed instance groups can work with load balancers to distribute network traffic to all instances in the group. If an instance in the group crashes, or is deleted by any action other than the instance group commands, the managed instance group automatically recreates the instance so that it can resume its processing activities. The recreated instance uses the same name and instance model as the previous instance. Managed instance groups can automatically identify and recreate unhealthy instances in a group to ensure that all instances run optimally. Regional managed instance groups are generally recommended over zone managed instance groups because they allow you to spread the application load across multiple zones instead of limiting the application to a single zone or having to manage multiple groups of instances on different areas. This replication protects against zonal failures and unexpected scenarios where an entire group of instances in a single zone fail. In that case, the application can continue to serve traffic from instances running in another zone in the same region. To create a group of managed instances, you must first create an instance template. Next, you will create a managed instance group of n specified instances. The instance group manager then automatically populates the instance group based on the instance template. You can easily create instance templates using the GCP console. The instance template dialog looks and works just like creating an instance, except that your choices are logged so they can be repeated. When you create an instance group, you define specific rules for the instance group. First, decide whether the group of instances will be single or multi-zone and where those locations will be. Secondly, choose the ports you want to allow and load balancing. Third, select the instance template you want to use. Fourth, decide if you want to autoscale and under what circumstances. Finally, consider creating a health check to determine which instances are healthy and should receive traffic. Basically, you're still creating virtual machines, but you're applying multiple rules to that group of instances. Let me provide more details on the autoscaling and health checks of a group of managed instances. As mentioned above, Managed instance groups offer auto-scaling capabilities that allow you to automatically add or remove instances from a managed instance group as the load increases or decreases. Auto-scaling helps your applications gracefully handle increased traffic and reduces costs when resource requirements are lower. You just have to define the autoscale criterion, and the autoscaler performs autoscaling based on the measured load. Applicable autoscaling policies include scaling based on CPU usage, load balancing capacity or monitoring metrics, or a queue-based workload such as Cloud Pub/Sub. The Resource Manager allows you to hierarchically manage resources by project, folder, and organization. This should sound familiar because we covered it in the Cloud IAM module. Let me refresh your memory. Policies contain a number of roles and members, and policies are set on resources. These assets inherit the policies from their parent, as we can see on the left. Therefore, resource policies are a union of parent and resource. Also, keep in mind that if a parent resource policy is less restrictive, it takes priority over a more restrictive resource policy. Although IAM policies are inherited from top to bottom, billing is accumulated from bottom to top, as we can see on the right. Resource consumption is measured in quantity, such as amount or time of use, number of resources or features used. Since each resource belongs to a single project, a project is the sum of the consumption of all its resources. Each project is associated with a billing account, which means that an organization contains all billing accounts. We explore more organizations, projects, and resources. Just to reiterate, an organization node is the root node of all Google Cloud resources. This diagram shows an example where we have an individual, Bob, who is in control of the organizational domain through the organization administrator role. Bob delegated privileges and access to individual projects to Alice, making her project creator. Since a project accumulates the consumption of all its resources, it can be used to monitor resources and quota usage. Specifically, projects allow you to enable billing, manage permissions and credentials, and enable services and APIs. To interact with cloud platform resources, you must provide project identification information for each request. A project can be identified by the project name, which is a human-readable way to identify your projects, but is not used by any Google API. There is also the project number, which is automatically generated by the server and assigned to the project. And there is the project ID, which is a unique ID generated from the project name. You can find these three identifying attributes on your Cloud Console dashboard or by querying the Resource Manager API. Finally, let's talk about the resource hierarchy. From the point of view of the physical organization, resources are classified as global, regional, or zonal. Let's take a look at some examples. Images, snapshots, and networks are global resources. External IP addresses are regional resources. And instances and disks are zone resources. However, regardless of type, each resource is organized in a project. This allows each project to have its own billing and reporting. Labels are a utility for organizing Google Cloud resources. Labels are key value pairs that you can attach to your assets, such as VMs, disks, snapshots, and images. You can create and manage labels using Cloud Console, Cloud, or the Resource Manager API, and each resource can have up to 64 labels. For example, you could create a label to define the environment of your virtual machines. Then define the label for each of your instances as production or test. Using this label, you can search and list all your production assets. Inventory purposes. Labels can also be used in scripts to analyze costs or to perform bulk operations on multiple resources. The screenshot on the right shows an example of 4 labels created on an instance. Let's look at some examples of what to use for labels. It is recommended that you add labels by team or by cost center to distinguish instances owned by different teams. You can use this type of label for cost accounting or budgeting. For example, Team Marketing and Team Research. You can also use labels to distinguish components. For example, Component Redis, Component Frontend. Again, it is possible to label according to the environment or the stadium. You should also consider using labels to define an owner or primary contact for a resource. For example, Owner, Gaurav, Contact, OPM. Or add labels to your resources to define their status. For example, state, in use, state, ready for deletion. Now it is important not to confuse labels with tags. Labels, we just discovered, are user-defined strings in key-value format that are used to organize resources and can propagate through billing. Tags, on the other hand, are user-defined strings that are applied only to instances and are used primarily for networking, such as applying firewall rules. For more information on using labels, refer to the documentation. Another way to optimize your Google Cloud spend is to use labels. For example, you can label VM instances spread across different regions. Maybe these instances send most of their traffic to a different continent, which could lead to higher costs. If so, you might want to consider moving some of these instances or using a caching service like Cloud CDN to cache content closer to your users, reducing network spend. We recommend that you label all your assets and export your billing data to BigQuery to analyze your spend. BigQuery is Google's fully managed, scalable enterprise data warehouse with SQL and fast response times. Creating a query is simple as shown in this screenshot, which you will explore in the next lab. Stackdriver dynamically discovers cloud resources and application services based on deep integration with Google Cloud and Amazon Web Services. Thanks to its smart default settings, you can have primary visibility of your cloud platform in minutes. This provides access to powerful analytics and data tools as well as collaboration with many different third-party software vendors. As mentioned above, Stackdriver offers services for monitoring, logging, error reporting, fault tracing and debugging. You only pay for what you use, and there are free use assignments so you can get started with no upfront fees or commitments. Now, in most other environments, these services are managed by completely different packages or a loosely integrated collection of software. When you see these functions working together in a single, complete and integrated service, you will realize how important it is to create reliable, stable, and maintainable applications. Tracking is important to Google because it underpins Site Reliability Engineering, or SRE. SRE is a discipline that applies aspects of software engineering to operations whose goals are to create ultra-scalable and highly reliable software systems. This discipline has enabled Google to build, deploy, monitor and maintain some of the largest software systems in the world. Stackdriver dynamically configures monitoring after resource deployment and has smart presets that allow you to easily create charts for basic monitoring activities. This allows you to monitor the platform, system, and application metrics by importing data, such as metrics, events, and metadata. You can then generate insights from this data via dashboards, charts, and alerts. For example, you can configure and measure uptime and health checks that send email alerts. A workspace is the root entity that contains the monitoring and configuration information in Stackdriver monitoring. Each workspace can have 1 to 100 monitored projects, including 1 or more Google Cloud projects and any number of AWS accounts. You can have as many workspaces as you want, but Google Cloud projects and AWS accounts can't be tracked from more than one workspace. A workspace contains the custom dashboards, alert policies, uptime checks, notification channels, and group definitions that you use with your monitored projects. A workspace can access metric data from monitored projects, but metric data and log entries remain in individual projects. The first Google Cloud project monitored in a workspace is called a hosting project and must be specified when you create the workspace. The name of that project becomes the name of your workspace. To access an AWS account, you need to set up a project in Google Cloud to contain the AWS connector. Since workspaces can monitor all of your Google Cloud projects in one place, a workspace is a single control panel through which you can view resources from multiple Google Cloud projects and AWS accounts. All Stackdriver users who have access to that workspace have access to all data by default. This means that a Stackdriver role assigned to a person in a project applies equally to all projects monitored from that workspace. In order to give people different roles per project and to control data visibility, consider placing the monitoring of those projects in separate workspaces. Stackdriver monitoring allows you to create custom dashboards that contain graphs of the metrics you want to monitor. For example, you can create graphs that display the CPU utilization of instances, the packets or bytes sent and received by those instances, and the packets or bytes released by the firewall of those instances. In other words, the graphs provide visibility into VM instance network traffic and usage, as shown on this slide. These graphs can be customized with filters to remove noise, groups to reduce the number of time series, and aggregations to group multiple time series together. Now, while graphs are extremely useful, they can only provide information while someone is looking at them. But what if your server crashes in the middle of the night or over the weekend? Do you expect someone to always look at dashboards to determine if your servers are available or have sufficient capacity or bandwidth? If not, you want to create alert criteria that inform you when specific conditions are met. For example, as shown on this slide, you can create an alert policy when the VM instance network exit exceeds a certain threshold for a specific time period. When this condition is met, you or someone else can automatically be notified by email, SMS, or other channels to resolve this issue. You can also create an alert policy that monitors Stackdriver usage and alerts you when you approach your billing threshold. Uptime checks can be set up to test the availability of your public services from locations around the world, as you can see on this slide. The type of uptime control can be set to HTTP, HTTPS, or TCP. The resource to monitor can be an App Engine application, a Compute Engine instance, a URL to a host or AWS instance, or a load balancer. For each uptime check, you can create an alert policy and view the latency of each global location. Stackdriver monitoring can access some metrics without the monitoring agent, including CPU utilization, some disk traffic metrics, network traffic, and uptime information. However, to access additional system resources and application services, the monitoring agent must be installed. The monitoring agent is supported for Compute Engine and EC2 instances. Stackdriver logging allows you to archive, search, analyze, monitor and send alerts on log data and events from Google Cloud and AWS. It is a fully managed service that works at scale and can import system and application log data from thousands of VMs. Logging includes archiving for logs, a user interface called Logs Viewer, and an API to manage logs programmatically. The service allows you to read and write log entries, search and filter logs, and create log-based metrics. Logs are only kept for 30 days, but you can export them to cloud storage buckets, BigQuery datasets, and Cloud Pub/subtopics. Stackdriver error reporting counts, analyzes, and aggregates errors in running cloud services. A centralized error handling interface displays results with sorting and filtering capabilities, and you can even set up real-time notifications when new errors are detected. Currently, Stackdriver error reporting is generally available for the standard App Engine environment and is a beta feature for the flexible environment of App Engine, Compute Engine, and AWS EC2. In terms of programming languages, the exception stack trace parser is capable of processing Go, Java, .NET, Node.js, PHP, Python, and Ruby. Stackdriver Trace is a distributed tracing system that collects latency data from your applications and displays it in the Cloud Console. You can monitor how requests propagate through your application and receive detailed performance insights in near real time. Stackdriver Trace automatically analyzes all traces of your application to generate in-depth latency reports that highlight performance degradation and can capture traces from App Engine, HTTP/S, load balancers, and applications equipped with the Stackdriver Trace API. Managing the time it takes for the application to handle incoming requests and perform operations is an important part of managing overall application performance. Stackdriver Trace actually relies on the tools used by Google to keep our services running on a massive scale. Stackdriver Debugger is a Google Cloud feature that allows you to inspect the status of a running application in real time, without stopping or slowing it down. Specifically, the debugger adds less than 10 milliseconds to the request latency when the application state is acquired. In most cases, this is not obvious to users. These features allow you to understand the behavior of your code in production and analyze its status for those hard-to-find bugs. With just a few mouse clicks, you can take a snapshot of the running application status or enter a new recording instruction. Stackdriver Debugger supports multiple languages, including Java, Python, Go, Node.js, and Ruby.